Good evening. Today we are going to see one problem that is on combined footing. So we have given, so we will go with given data. Two columns are given A and B, and working loads are given 750 and 800. So we have given data. PUA we have 1.5 into 750, so 1125 kilonewton. PUB 1.5 into 800, 1200 kilonewton. Then we have column size 380 by 380 mm. Then distance between two columns 2.5. Ultimate SBC 1.5 into 225, sorry, into 150. 225 kilonewton per meter square. M25 and FE415. So we have step 1, size of footing. So now we have given two columns. So load is around the same. So when load is same, it is better to assume this value that is beyond any one column 1 meter. Generally, the column with a lesser value of axial load, we can provide projection beyond column 0.5 to 1 meter. So this is 1 meter. Then from center, we have given this distance as 2.5 meters. Load on this column is 1125 kilonewtons. Load on this column, we have 1200 kilonewtons. We have CG of column will be somewhere here 1125 plus 1200 will be 2325. And this distance from center, let us we will consider it as X bar. Now concept we have CG of column load. CG of column load equal to CG of footing. Equal to CG of footing, or CG of column load and footing coincide. And therefore, we have L by 2 is equal to 1 plus we have to add this distance 0.19 plus X bar. Now, how to find X bar? We have to use Varignon's theorem, and we have this Varignon's theorem, that is moment of component about a point equal to moment of resultant. So we have moment about A equal to 0. So 1125 into 0 plus 1200 into 2.5, and that is equal to 2325 into X bar. And if we will calculate this value of X bar, then we have this value 1200 into 2.5 divided by 2325, it comes 1.29 meters. Now this centroid means we have this value as L by 2 and this value L by 2, but it should coincide. And therefore we will get L by 2 is equal to 1 meter, which is projection beyond column, plus 0.19 meter, which is half the column, and plus X bar. And then we will get L by 2 is equal to 1 plus 0.19 plus 1.29. And from this we will get 0.19 plus 1.29 plus 1, so it will be 2.48 meter. And therefore, L will be equal to 4.96 meter. Therefore, provide length of footing equal to 5 meter. Length of footing equal to 5 meter. Now we have to find width. And for this width, we have to find area required. So now we have total load on footing in the same way as isolated. So total load on footing. So we know load on column plus 10% as self weight. Load on column plus 10% of column load, which will be self weight. So this is self weight. And therefore, we will get this value equal to 1.1 into 2325. And this value is equal to 2557.5 kilonewtons. Now we know ultimate SBC, and therefore area of footing required. So area of footing required equal to total load upon ultimate SBC divided by ultimate SBC. And then we will substitute the values. So we have 2557.5 into 10 raised to 3 upon 225. And from this we will get value that is 11.3 meters square. And we have width of footing equal to, therefore, width of footing equal to area upon length, and we have this value 2.27 meter. And therefore, footing dimensions we have 2.3 meter by 5 meters. And actual bearing pressure then, actual bearing pressure equal to, now this is column load, you have to keep in mind, this is most important, column load upon area of footing. Column load we have 2325 divided by 2.3 into 5, and we have this value 202.17 kilonewton per meter square less than ultimate SBC 225 kilonewton per meter square. Now net upward soil pressure, net upward soil pressure, along the length, so we have to find UDL along the length, and therefore we have to multiply it by actual bearing pressure multiply by width, as it is required along the length, so we have to multiply it by width, and this value comes 464.99 kilonewton per meter now, and approximately we will consider 465 kilonewton per meter. Then we have next step, that is SFD and BFD. So we have step 2, SFD, BFD. We have, if I will draw diagram of loading, so we have loading in this fashion, Now I will not show all calculations of SFD, BMD. You are in position to calculate it. If you have any doubt for this, you can WhatsApp me. Then I will send you answer of this. So we have this as 465 kilonewton per meter. Now our load will act, column loads will act. That is, first column load on left side will be 1 meter projection and 0.19 its value, half of the width. So this is 1.19. Then we have 2.5 meters. And then we will get next value. So that will be 5 minus 2.5 minus 1.19, and it comes 1.31 meters. And now we have SFD. So first we have upward. So we have this value upward, and that is 553.35. So this value we have calculated 465 into 1.19, and it comes 553.35. So this is 553.35. Then we have bottom value 571.65. So we have 553.35 minus 1125, and this comes 571.65. So this value is 1125, and this value is 1200. Then we have 590.85. So we have this value here, that is 590.85, and this value we have minus 575.5. So we have minus 571.65 plus 465 into 2.5. Then we have 1200 below. This value comes 609.15. And then it will be 0. Now this value we have 590.85 minus 1200. As it is down, so this will be minus. So this is my SFD. This is the loading. And then we have BMD. So we have WL square by 2 from both sides. And then we will have this value that is equal to WL square by 2, 329.24 under the column. At 0 shear force, actually this value comes very less, 22.14. From another side, it comes sagging, and from left, it comes hogging. So it is very less. So we have to provide minimum actually moment. So do not go in much calculation. So this is 399 kilonewton meter, and then we have 0 kilonewton meter. This value we have 465 into 1.31 square by 2, and this value we have 465 into 1.19 square by 2, and this comes 22.14 from left, and this value we have calculated, that is 0 shear force. We have 0 shear force. This is 1.23 meters. And therefore you can find this 1.19 and 1.23. We have this total value 2.42. And by using this value, we are in position to find this bending moment. That is 465 into 2.42 square by 2 minus 1125 into 1.23. And we have, this is our bending moment diagram. So now once we know this diagram, we have to find depth for bending moment. So we have step 3. Step 3, depth from bending moment. And for this, we have to find value of RU max first. So we have RU max. We have same step. If you will see, only changes in calculations. So we have 0.36 FCK KU max in bracket 1 minus 0.42 KU max. And as we have M25 and FE 500, so we have this value 0.36 into 25.46, 1 minus 0.42 into 0.46, and we will get this value 3.34 Newton per mm square. Knowing this value, we can find required depth. So we have D required equal to under root of mu max upon RU max into B. Now we have mu max. Now if we will go back and see bending moment maximum value, so we have maximum value of bending moment. We need not require to consider that sign, hugging or sagging. We have to consider maximum 399. So we have 399 into 10 raised to 6 divided by RU max is 3.34 and B we have 2300. And we will get this value that is equal to 227.19 millimeters. And we have to go for 150 actually. We have to add around 200 in it, same as our isolated footing. So always go on higher side. So provide overall depth, and that is equal to 450 millimeters. Because check should be satisfied. That is check for shear, one way and two way. Here we have to go only for two way. Now we have D equal to 450 minus 60. This D, then we will get it as 390 millimeters. Now next we have step 4. Check shear, check two-way shear. One way we will not go. And then we have this will be tau UC first we have to find, which will be equal to Ks into tau UC dash. As we have Ks dimension of column that is same, so we have 380 by 380, and that comes 1.5 greater than 1, and therefore value of K we have 1, Ks. And tau dash UC is 0.25 root FCK. FCK we have 25, so 0.25 root 25, and it will be 1.25 Newton per mm square. And substituting this value, we have 1 into 1.25, and therefore we have tau UC 1.25 Newton per mm square. Now we know that shear will act at d by 2 from face of the column. If you will draw dimension of this column, so you have to go always for higher load. So we have column that is 380 by 380, And beyond this, we have d by 2, d by 2. So we will have d by 2, d by 2. So it will be 380 plus dy we have 390. All we have same because square column is there. And therefore we will get size of critical section, or size instead of this I will say side of critical section, and that is equal to 380 by 390, and this comes 770 millimeter. As it is square, so we have perimeter at critical section. Same steps we have perimeter at critical section, and that is equal to 4 into 770, and we have this value 3080 millimeters. So knowing this value, we can find area resisting shear. So area resisting shear, and that is perimeter into depth. Now again we have uniform depth, so perimeter into depth. And perimeter we have 3080, depth is 390, and we will get this area 120 millimeters square. And then we have shear strength equal to shear stress into area. So shear stress into area. Now shear stress we have 1.25, and area we have 120, and we have this value 1501.5 kilonewton, and we have design shear. So design shear, and this is equal to column load minus load due to upward pressure in critical section, in critical area. Column load we have to always go for maximum value. So 1200 minus, we have intensity 202.17, and area we have 0.77 into 0.77, because we have this value 0.77, and we have this shear force 1080. So we have this value, that is 1080.13 kilonewton, which is less than shear strength 1501.5 kilometers, and therefore safe. Then we have area of reinforcement. So we have step 5. Now this actually you can do it. Step 5. So area of reinforcement. Then we can have this AST equal to, we have to use formula 0.5 FCK upon Fy in bracket 1 minus root of 1 minus 4.6 mu upon FCK BD square into B into D. And we have to put one by one value. First we can say that is under column B. Under column B, and we have AST equal to 0.5 into 25 upon 500. And then we have to put 1 minus root of 1 minus 4.6. MU is 399 into 10 raised to 6 divided by FCK 25, P 2300, and D we have 390 square, and multiply by 2300 into 390. And from this we will get value 2491.48 millimeters square. Then under provide 16 millimeter bars, and numbers we will get equal to 2491.48 upon 201, it comes 12.4. So we have to provide 16 diameter 12 bars. Sorry, 13 bars. This is under column A. And then for hogging bending moment, we have to provide AST minimum. Actually, above steel also we have to check it for AST minimum. And we have this as 0.12% of B into capital D, that is most important. And this comes, B is 2300 and D capital is 450. And this value comes 1242. And these both are greater than this. Column A actually I have not mentioned, that I will mention afterwards. And we got this 13 bars. For this hugging bending moment, we have 7 bars of 6 mm diameter, 16 mm diameter. And then last we have under column A, we have this as AST. I got this value of AST, and that is 2033.9. And I have provided that is 11 bars of 16 mm diameter. Now actually the reinforcement due to hogging, we have to plot it at top. So due to hogging, we got that value, that is 7 bars. So you can curtail these bars alternately, 1, 2, 3, 4, 5, 6, then 7. This is top reinforcement. Bottom we have to find, that is under column B, and under column A we have to provide it, that is till your zero bending moment. That values actually we have to find out zero bending moment, and that we can find by considering this. So here you can write zero bending moment, and you will get, I have this value actually, zero bending moment, first value I got 2.11 meters. And that we can consider this as X, and then we can have 465x square by 2 minus 1125 into x minus 1.19 equal to 0, and we will get 2.11 meter. And this value actually, this again is 465. This is very large value of intensity, and therefore I have calculated it. I have this value as 2.58 meters. So just check it, And then you have to provide reinforcement in this fashion. For column B, we have this as 13 bars. And then you have to provide till that 0, 13 bars alternately. You have to go this bar. So we can have alternately cut. So 11 and 13, so we can go same. So 1, then we can curtail it second, then we can have third, then fourth, then fifth, then sixth. Likewise, you have to provide 11. I will not go for this. And then you have to find actually transverse reinforcement. Transverse reinforcement. Now for this one, you have to find bending moment. Now we have again cantilever and UDL for this. So we have seen, we have this value that is 202.17, and we have to multiply it by length now because we are finding it along the width. So we have to multiply it by 5. And this distance we have cantilever portion beyond face of the column, and beyond face of the column, we got this value as 1.31 minus 0.19. So 1.31 minus 0.19, so 1.12 meters. And then we have 202.17 multiplied by 5 comes 1010.85. And then WL square by 2, so we will get MU, that is equal to into 1.12 square by 2, it comes 634 kilonewton meter. And then you have to find AST for this, and that AST you have to provide along this throughout. Now I will not go for these calculations, just check it, and this will be my transverse reinforcement. And likewise, we have to solve this problem. They have mentioned there, do not go for check for one-way shear. So I have not considered that one-way shear. Now I cannot actually go for more videos because I have family issue, and whatever possible from my side, I tried hard and I posted this video. If you want anything, you can call me. You can send on a WhatsApp. I will try to answer for you. Now I will stop here only. Thank you.